Well, it looks like it's time. Welcome back, everyone. So with where we're at so far, we made a early start on the mean value theorem, section 4.2. And as far as the other sections go in chapter 4, this is probably going to be the shorter section. So we're going to make some headway into the very next section, how the derivatives affect the shape of a graph. Really, section 4.3 is continuing a theme in section 4.1, where we're going to focus specifically in 4.3 on finding the local minimum, local maximum values of a function, also finding where a function is increasing, decreasing, and look into other issues like concavity as well. For the moment, we're going to be studying the mean value theorem, finishing off this section. We haven't yet introduced the mean value theorem, even though we started this section. But what we really looked into was Rolle's theorem, which guarantees the existence of a critical number. So that's where we're going to pick up. And that was a pretty short announcement to start us off for today, but any last questions or thoughts at all, folks, before we start? Okay, let's jump in. So we got halfway through the very first problem, where all we did was verify the three hypotheses of Rolle's theorem. But just as a refresher, let's take another quick look at all this. For Rolle's theorem, we assume f is a function satisfying the three hypotheses, that it's continuous on a closed interval specifically, that's also differentiable on an open interval, and that at the endpoints of that closed interval, the function values take on the same common value. As a quick graph, this is about what it would look like. It tells us that there will be some number c between a and b, we see it here on the graph, for which the derivative will be zero, but a zero derivative just means horizontal tangent line. So it's in this way, Rolle's theorem tells us there will be a critical number, and it gives us a neighborhood of where that will occur. Notice it'll occur in the open set AB, so it'll never occur at A. That's not what the conclusion is for Rolle's theorem. There might be a critical number there, but in the conclusion of Rolle's theorem, it's going to be specifically between A and B, not at the endpoints. So that's Rolle's theorem. We verified three hypotheses for one specific function, a polynomial, in a strange factored form. But any questions with just the statement of the theorem so far? Okay, well, let's take a look into finding that critical number c that satisfies f prime at c is zero. First step we did, we'll have to do this on the homework as well, was verify that our function, here it is, it's a factored form of a polynomial, degree 7, that's to be continuous, but we saw in section 2.5, polynomials are absolutely continuous on the entire real number line. So if we restrict to the closed interval 0, 7, it's still continuous there. If we differentiate it, we still get a polynomial, and the derivative of a polynomial exists at all real numbers, so it'll also exist on 0, 7, so that verified hypothesis 2. And for this particular polynomial, it turns out that, sure, if you evaluate the f at a part, the f at b part, that's evaluating f at 0, f at 7, it comes out to 0 on both of these, which tells us f of 0 is in fact equal to f at 7. So that was the final hypothesis we had to check. Now we're at this part. Since we know that Rolle's theorem applies to this particular polynomial, there will be some number c between a and b, which is 0 and 7 in this problem, for which the derivative is 0 at that number. So all we're doing now is finding that number c in the conclusion of Rolle's theorem. So that's where we left off. Any questions at all, folks, before we start tackling this problem here? Okay, as far as finding this number, really the trickiest part is that this bit of information there. So our conclusion C is going to be in the open set from 0 to 7 for this particular problem. So we have to make sure we state only that number or those numbers within that particular domain from 0 to 7, excluding the boundary points. But beyond that, all we're really doing is finding a critical number, just like we did in the prior section. Step 1 in finding a critical number is to take your function and differentiate it. Let me copy it down here just so it's more easily available. F of x is x cubed times x minus 7 to power 4. We need to differentiate this function, but that's just going to be a product rule setup. I'm already using up a lot of colors, so we won't color code this one. The derivative of f at x through the product rule states first differentiate x cubed. That'll be a 3x squared. Then copy x minus 7 power 4. The new term, first copy x cubed. Then differentiate this function, x minus 7 to the 4th power. This one's a chain rule, but this is one of those chain rules where we mentioned it's not going to cause a big deal if we did this one, say, mentally in our head, because of the derivative of the inner function comes out as a 1. Let's put it down on paper, just because we're still practicing the chain rule. That one's always really tricky. When we do the chain rule, we differentiate the outer function, the degree 4 polynomial, write it to degree 3, chain on a new derivative, which is going to be the derivative of x minus 7. But this is the pattern. We just throw x minus 7 in both of those placeholders. And it just so happens that derivative of x minus 7 for this function is a 1. But still, always be really wary, like we mentioned last class. If that was 3x minus 7, that derivative matters because it'll turn into a 3, not a 1. But if you saw ahead, you knew the derivative was going to be a 1, then this is something you don't have to put down on paper. That'd be a good mental shortcut to take. So in cleaning up this derivative, it comes out as 3x squared, x minus 7, power 4 multiplied, plus 4x cubed times x minus 7 to power 3. Now we need to solve an equation, the derivative set to 0, which means we still simplify this even further. We need to factor it down as much as possible, which boils down to this problem: take out the greatest common factor. We can factor out an x squared. We can factor out x minus 7 to as high as the 3rd power. When we factor those out, that's going to leave 3 times x minus 7 to power 1, so just x minus 7. Here we'll get plus 4 times x is all that's remaining after factoring. Next thing we should do is just simplify the thing on the inside. And let me carry this down so we can see it as we continue to scroll. This one's taking a little bit more space than expected, probably because of the hypotheses verification phase. So next stage, we have x squared times x minus 7 to 3x minus 21 plus 4x. And we're about there. Now it's x squared times x minus 7 times 7x minus 21. So that's our entire derivative, f prime at x, simplifies all the way down to that through this long chain of equalities. We want to set it equal to 0, and we can do it just right here. Now set equal to 0, and this is all f prime at x set equal to 0, highlighted in yellow. Because it's in a factored form, we can just read off the factors. This will imply on the next line, x is 0 from the first factor, plug 7 here, and the equation balances as 0 equals 0. If you plug 3 here, or set the whole thing equal to 0 and solve for x, either way, you get x is 3, and it becomes 0, balancing to 0 equals 0. And those are the solutions to f prime at c equals 0. This is not the solution to the whole problem, though. We have to go a step further and be really careful with our analysis. The conclusion to Rolle's theorem is that there's a number c in a particular range, and that's the one and only number, or possibly more, but I think it's 1 on this one, that we're looking for. So let's scroll up for just a moment. We remind ourselves right here, find all numbers c satisfying conclusion of Rolle's theorem means c must be inside 0 to 7, excluding the boundary points. So that means 0 and 7 are no good for this. They are the boundary of the domain, and our conclusion is that, therefore, C equals 3 is the only number satisfying the conclusion. Because it's the only number that's specifically between 0 and 7. So that's the full tour of getting through Rolle's theorem. The last part is definitely a bit tricky because it feels like we're done right at that stage. They're all three critical numbers, but when it's talking about specifically the conclusion of Rolle's theorem, that number was the only one that made the cut. Let's highlight there just to make it look extra special. But any questions at all, folks, getting through the conclusion here? Okay, Rolle's theorem probably feels a little bit weird in this section, 4.2. We're doing two technical theorems. Here's the first, Rolle's theorem. But the title of the section is the mean value theorem. One good reason of doing the Rolle's theorem here is if we want the mean value theorem, it's pretty similar to what this is saying, but we make one small change on the hypotheses. We delete part 3, which is pretty restrictive. We had to make the domain be perfect to get the function to match on the boundary points f at 0 equals f of 7. So we delete part 3, and then that's going to change our conclusion here. Caleb says, why do we transfer from the closed interval to the open interval? Well, that's a pretty good question, and it really has to do with part 2 right here. F is differentiable on the open interval from a to b is a requirement only because when we went to go to define the derivative, the definition of the derivative looked like this. F prime at x equals the limit as h goes to 0 of f at x plus h minus f at x, all divided by h. So that's our derivative. And here's one weird technical issue. F prime at a does not exist. Just flat out won't exist at all. Why is that? It's because this was a double-sided limit. As h goes to 0, you had to get a value as you got closer and closer to the left boundary point, a right there. But that's a single-sided limit. That's as h approaches 0 from the right-hand side only, which is really kind of weird. This didn't come up in the continuity section, but in the continuity section, notice what we did here. We defined continuity from the right, continuity from the left, and so we could talk about continuous on an interval. It's continuous at every number in the interval, and if we are saying at the endpoint, say right at A, we mean continuous from the right specifically, continuous at the endpoint B, we mean continuous from the left. We had those two definitions, but the same thing doesn't apply to the derivative. For a derivative to exist, you have to take a value that's inside the closed set from A to B, not at a boundary point. So if you make it an open interval, the derivative will exist guaranteed. So that's the major reason for why it has to convert to an open interval there. Derivative doesn't actually exist on the boundary of the domain. If the function ends at 0, the derivative doesn't exist there unless we define single-sided derivatives, which our textbook never did. So that's kind of a long answer for a pretty technical issue. Does that help clarify that question there? Okay, I would say the short answer to it is it has to be only going from a closed set, because we have continuity from the right and the left, to an open set, because derivatives don't exist on the far left boundary or the far right boundary of a domain, is the short answer to that kind of issue there. So Rolle's theorem is just forced to be defined in this kind of way. Other questions at the moment? Okay, well, For the next theorem, we're going to extend from Rolle's theorem into the good old mean value theorem. So here it is. It has two hypotheses. F is continuous on a closed interval. That's the same as hypothesis 1 in Rolle's theorem. The last hypothesis is that it's differentiable now on the open interval. Same technical issue there. Open interval only because our derivative doesn't exist on a boundary value A or B. So we're saying continuous on a closed set, differentiable on an open set. Condition 2 is exactly the same as Rolle's theorem, but we peeled off a third condition. We don't want f of A to be equal to f of B. That's highly restrictive. So people wondered, what happens if you just take that off? If you lift that restriction, what does the geometry look like for the graph that we put on the first part of the notes? And what does the conclusion look like? Here, the conclusion was the derivative is 0, a critical number. But now the conclusion becomes this. F prime at C is f at B minus f of A divided by B minus A, where the A and B came from the closed interval at the very top. So there will be a number C in that interval. This part is verbatim the same as Rolle's theorem, and this is the change. If f at A is not f at B, you get this. If they are equal, it's 0 in the numerator, and it just becomes Rolle's theorem. So Rolle's theorem is just one special case of the mean value theorem altogether. So that's what the mean value theorem looks like, looking at it from just a purely analytical side. To get a better feel for it, let's draw a picture to see what's going on geometrically, just like we did for Rolle's theorem. So I wanted to draw down a similar picture, focusing really just on quadrant 1 like we did before, just to make the picture more simple. We'll have a function starting off at A. We'll end at B, so it's going to be defined on this closed interval. It must be continuous. I'm going to draw something that's differentiable, so no corners or cusps. It'll be differentiable from A to B, and this time I can start a point here. Rolle's theorem says it has to end right at that spot, but let's just let it go higher this time. Or lower, you can put it wherever you want. I'm just going to draw one diagram, so I just chose to let it go up. So we have a function value at f at A, another function value at height f at B, and the curve is going to look like this, just some random generic curve, increases for quite a while, then eventually comes down, lands on that point there. So here's our function, y equals f of x. So the conclusion is, got a lot going on, right? Conclusion for Rolle's theorem is you had a critical number, but now it's changed to this entire thing. But we've seen this kind of stuff all the way back in section 2.1. If you look at f of B minus f of A divided by B minus A, this is just the average rate of change for y equals f of x from x equals A to x equals B. It's literally the slope of this line. If we draw a line that goes like this, I kind of missed, maybe we can correct it here. If we draw a line that goes about like this, there we go, let's just fix it. Then the slope of this line is exactly f at B minus f of A divided by B minus A. If this was, say, a position function, we would have just called m average velocity. So that explains what the right-hand side, the fraction, is really all about. Now we tie in the derivative. But any questions with the diagram as it is so far? Okay, let's see if we can manipulate this just right. I'm going to copy the line. So here's my second copy. I wanted to do it just like that because I don't want my line to change its slope. And notice you can put it anywhere, but wherever you put this line, if I put it here, it's not a tangent line, it's intersecting the curve in a weird way. If you move the line just right, keep on dragging it up, until you get to just one certain spot, say right around here, it becomes a tangent line. Might not be perfectly placed. Let me go just a little bit higher. Right about at that spot, a little bit lower, just settle on one spot. That should do the job. Let's just stick with that. At that spot, let me just overwrite it with this line. This becomes a tangent line. A tangent line intersects the curve y equals f of x at this point right here in blue, and the x-coordinate to that point is the number c, strictly between a and b. Now that tangent line has slope m, which is going to be f prime at c. Well, that's what the derivative is. It's the slope of the tangent line at a specific point when you plug in c. So m is f prime at c. But at the same time, f prime at c, well, this had the same exact slope as this line. We literally copied it to drag it up so the slope didn't change. So that f prime at c is going to be equal to f at b minus f at a divided by the b minus a that we had there. So that's where the conclusion comes from in the mean value theorem. All it really is literally is taking Rolle's theorem that had these points at the same height, just drag a point up, and that's what the new derivative is. No longer zero, it's changed into the average rate of change for the entire function now. So the mean value theorem is telling us that if you compute the average rate of change, there is a number within the open set from a to b where the derivative will exist that actually takes on a derivative exactly equal to that average rate of change. So the derivative is equal to the average rate of the change of the function somewhere inside the derivative. It has to happen. For that to be a guarantee, a strong guarantee, we need continuity on a closed interval and differentiability on the open interval. So that's the tour through mean value theorem. What we're going to do next is apply it in a concrete example. Any questions or comments at all, folks, with what we see here for mean value theorem? Okay, well, we're going to soon be in chapter 5, where the topic is all about integration. And we made this comment before that when we were in section 4.1, one of the theorems called the extreme value theorem was actually a core component to something called the fundamental theorem of calculus. And that's really the big takeaway with the mean value theorem when we get to that chapter. Let's say it here just as a preview. This is a core part of the proof to the fundamental theorem of calculus, which we will be seeing quite shortly. Next week, we'll be looking into that fundamental theorem. So we'll come back to this, see how these ideas relate just with the extreme value theorem. But for the moment, we're just practicing the mean value theorem for its own sake. So let's take this whole theorem. Here it is copied once again down below, compactified just a little bit. We have a conclusion that there's a number c in the open interval from a to b, such that the derivative equals the average rate of change is the best way to say it. So AB comes from the closed interval where it's continuous, and we must have differentiability on the open interval. So this will be very similar to what we did on example 2. Only difference now is we're applying mean value theorem to the brand new function. Now here's the function, not anything too major. It's a function composition, so the derivative does require chain rule. We want to verify that this function on this closed interval from 0 to 1 satisfies the hypotheses of the mean value theorem. So this is something that we'll have to write out just like we're on the homework, just like we're doing here. First thing we need to check is continuity. But we don't have to get too fancy. We can just use what we already know about continuity. And section 2.5 is a great one-stop shop for that kind of information. So scroll down all the way to the characterization theorems for continuity. They start off on theorem number 4 up to theorem number 7, 8, and 9. We're told a certain catalog of functions are continuous everywhere in their domain. And one of them, let's take a look, was the exponential functions. Our example was 7 to the power of x. But e to the power of x is exponential, so we have one exponential function there. Negative 2x makes it a function composition, but that negative 2x is a polynomial, which is also continuous. Then theorem 9 says if one function is continuous, g, think of g as negative 2x, and the other function f is continuous, think of that as e to the x, then the composite function f of g is also continuous at that number a. So we can make a really short statement here. We have theorems that support all this. We have by theorem 7, y equals e to the x and y equals e to the negative 2x is continuous. It's continuous on the entire real number line. But if we restrict our function to a closed interval from 0 to 1, it'll still be continuous there. So the component functions are continuous on that interval. And now we can say, and by theorem 9, this is when we compose the functions. If we say f of x equals e to the power of, hang on, I think I wrote that weird. I have e to the x on the first one. I think I was thinking for the second one, negative 2x like that. So negative 2x was going to go on the inside. I don't know why I put a base e there. Sorry for that distraction. So one function is e to the x. The other function is negative 2x going in place of e. So a function composition. That's why the chain rule applies. And theorem 9 says when you compose functions together that are already continuous, they stay continuous. So this is also continuous on 0 to 1. So essentially, just like we did on the first example 1, we cite theorem number 7 and anything else that we need to cite from that section, 2.5. I should say that right here. Forgot to mention in section 2.5, theorem 7 specifically. So we absolutely have continuity of this function. It's a nice, well-behaved function, even if we restrict the domain to 0, 1. There's no holes, jump discontinuities, infinite asymptotes whatsoever. Next thing we'll check is differentiability. And the easiest way to check differentiability is to just differentiate it. So let's go back here, take the derivative of that function, f of x, let me just write here for easier visual reference, is e to the power negative 2x. That implies the derivative f prime at x is a chain rule derivative. We take the derivative of the base e exponential. Looks like that. It's itself with the same input going in. Chain on the derivative of that input. The input is negative 2x, so it goes in both of those slots. And so this derivative, I'll write to the base e exponential first, is e to the power negative 2x. Multiplied by the derivative here, but that's just a negative 2. I'll put the negative 2 coming in first, since that's the way we would typically write that. So that's our function. The derivative is negative 2 e to the power of negative 2x. And we can say here, this shows f prime of x exists for all x in the open interval from 0 to 1. That's the interval where we're going to get our conclusion. Well, how do we know that? That's our complete derivative right there. It takes on that form. And you're free to plug in any value for x whatsoever and get a definite answer for what the slope will be. So our differentiation rules gives us this as the derivative and now completely exists. The only way this could ever go bad is if something like this happens. Like we saw in section 4.1, we took a nice function that it was continuous on the entire real number line from negative infinity to infinity. But when we differentiate this function, section 4.1, it produced a denominator. And there's one excluded value, you cannot plug 4 into the derivative, so the derivative did not exist at one particular point. So if we try to do the mean value theorem on this, on any open interval, or a closed interval rather, that contains 4, the hypotheses would not be satisfied. But for this one, you can plug in any value for x, you're going to get an answer for the slope of the tangent line. And so we have that conclusion, f is differentiable, or in other words, we said f prime at x exists for all x in the domain. And that's it. Those are the only two conditions. So we can say right here now, therefore, f meets the hypotheses of the mean value theorem. So what we'll do next is find all numbers C that satisfy the conclusion to the mean value theorem. So now we're at this part. C must be between 0 and 1. It doesn't hurt to say it once right here. C is in 0, 1, so now we have a reminder. Those are the only plausible values. And the conclusion of the mean value theorem is C satisfies that whole equation there. Well, the mean value theorem guarantees existence. Now we have to find it. Any questions at all, folks, before we begin? Okay, in solving for this, finding the value C that's equal to the average rate of change of the function on the domain from 0 to 1, a good first step is take the derivative. But we did it. Here it is. We did the derivative on step 2, verifying the conditions. So that's kind of nice. That did two things at once. The next thing you'd want to do is just compute the average rate of change. So let's do it right here. So we have that f of b minus f of a divided by b minus a. Well, in this problem, we have that a is 0, b is the 1. So they're just the values that are on the endpoint of the closed interval where the function is defined on. So down below here, this would become f at 1 minus f at 0 divided by 1 minus 0. The 1 minus 0 is nice. That means we can just drop the denominator. It's a division by 1. Now, when we say f at 1, we don't mean plug 1 here. That's f prime at x. We indicate that by putting the derivative symbol there. We mean go back to the original function, f of x. Plug a 1 into that one. So f at 1 is going to be e to the power of negative 2 times 1. When it says f of 0, that's going to be e to the power of negative 2 times 0. So that's the average rate of change. We have to do more with it. We're going to solve an equation, so we'll simplify as much as possible. This becomes e power negative 2 minus e to the power of 0, and e to a power 0 is just a 1. So that's our part that's in yellow, the right-hand side of that equation that we want to solve. Once again, we have the left-hand side. We started with f prime at x. We ended up here. I'll leave it as x for the moment as we solve the equation, but then you can call it c when we go to the conclusion at the very end, if you prefer. So here's our next step right after. Before we go to the equation solving side, any questions at all? Just getting that e to power negative 2 minus 1. Okay, let's continue going forward. We have all the good components we want for the conclusion to the mean value theorem. We're just going to take this part, f prime at x, equate it to this part, the average rate of change of the equation, and now we're solving that equation there. So this becomes left-hand side, I'm going to put in as a variable x, negative 2x, negative 2 e to the power negative 2x equals e to the power negative 2 minus 1. Let's highlight that in yellow just to convey where all that stuff came from. Now it's just an ordinary equation solving. We've seen equations like these. If you're solving an exponential, first get the base c exponent isolated. So divide by negative 2. We'll have e power negative 2x equals e power negative 2 minus 1 divided by negative 2. You can multiply both sides by negative 1 to make that a positive 2 in the denominator. Makes it a little slightly nicer, but I'll just leave it just like that. Next step, take the natural log of both sides. When you do that, you get just negative 2x on the left equals the natural log of e power negative 2 minus 1 over negative 2. Then divide by negative 2. So this becomes x equals negative 1/2 times the natural log e power negative 2 minus 1 divide by negative 2. So my claim is that's the number c for which if you plugged this into the original derivative right here in yellow, you're just going to get that, the average rate of change, e power negative 2 rather, minus 1. But once we get this far, this is a kind of bizarre number to get any feel for. Is that big, small, positive, negative? I have no idea when I'm just looking at something like that. And we have to be careful because in the conclusion, it has to be specifically within a to b as an open interval. In other words, for our problem, it has to be within 0 and 1. So this is a good step to go to a calculator, approximate this, and see if we're on the right track. You have negative 1/2 times natural log of a fraction, e power negative 2, minus 1, divide by negative 2. It comes out to about 0.42 approximating. And that's good news. It's not a guarantee that we didn't make a mistake, but that's pretty good numerical evidence that we're on the right track. There's only one number c that satisfied the hypothesis of being between 0 and 1, and so that did the job. So say here, to finish up the problem, this is the number c in the conclusion. The conclusion to the mean value theorem that we have down below here. So that's the mean value theorem. It's effectively saying the average rate of change occurs somewhere within the domain of the function, not at the boundary points. And this is just the language that we say that in, using derivatives. Well, let's see if we can zoom out on this problem. Any last questions or thoughts at all, folks? Seeing the lay of the land for the mean value theorem? Okay, again, there's oftentimes two sides to the story. This is the analytical analysis that we require to get the exact number c, but also there's the geometry of what goes on. That number c has to have a slope for the tangent line that's the same as what this slope would be, the average rate of change, this line right here. And that's something we can check right here. This is something that you'll be asked to take a look into in the homework exercises. So let's do it here just to show what that would look like. If you're doing this as a homework problem and you're doing a further check on it, what you would do is get a graphing utility of some kind, put in the original function, which is e negative 2x. We have to be very specific on the domain, that closed interval. So in Desmos, we use a curly brace, put x between 0 and 1. And that's our whole function right there. Let's zoom in on that thing. Now to match what we did above when we were drawing out the geometry for the mean value theorem, let's add a couple more lines. We had an orange line that went from here to here. Let me draw that the best that I can. That'll do the job. So there's a line. Now, if you imagine this line copied and just drugged down in a rigid way that doesn't change the slope, it would probably intersect somewhere right around here. And the slope of these lines, just be forgiving because this is freehand drawn, so it's not perfect, but those slopes would be about equal. Then it became a tangent line when we intersected here. If we go down, that number is C, which is approximately 0.49. I know I shouldn't have deleted that prior line. Let's put this on here as well. -1/2 natural log e power -2 minus 1 over -2. That came out to 0.42. So it looks like I'm a little bit closer to the 0.5, but for a freehand sketch, that's pretty close. So this would give me graphical evidence that we do really have the right number C when we produced that value. So that's what it looks like to verify our answers for the mean value theorem. We'll put it here back on the notes just for a reference. And then we'll take one more look at the mean value theorem before we go to the next set of notes. But any last questions or thoughts, folks, before we try the last example of this set here? Okay, well, here's the final problem for the notes. Let's take this down with us as we go. We have a new function we're analyzing. F of x is x minus 3 to power -2. That's a nice format to write it in. It's just ready to go to differentiate. We're told here to show that there is no number C in the domain, the open interval, 1 through 4, such that the derivative of f at C is the average rate of change, f at 4 minus f of 1 divided by 4 minus 1. So we're trying to show there is no such number. The number cannot be found. But then we'll do a follow-up look at this and say, why didn't it contradict the mean value theorem, where the mean value theorem says there will be a number? Well, that's the whole problem so far. First thing we're going to do is compute this average rate of change, f at 4 minus f at 1 divided by 4 minus 1. We're trying to show that equation has no solution, so we just need to look at both sides of the equation. So first, f at 4 minus f at 1 divided by 4 minus 1 is a good amount of algebra arithmetic already, computing this. We're plugging 4 here. We haven't even computed the derivative yet. So this will turn into 4 minus 3 power -2 minus, now plug in a 1 minus 3 power -2, all of which is divided by 3. Now this is the nice part right here. This becomes 1 to the power -2, and that's just 1 altogether. Minus, this one gives us more steps. This is going to be -2 to the power -2. Now it's kind of like an exponent law review problem at this stage. Divide by 3. So we can simplify this to 1 minus, throw that into a denominator, forcing the exponent positive. 1 over base -2 to +2 exponent over 3. And just keeps on going. Let's wrap over to here like a typewriter to the left side. Now it's 1 minus 1/4 over 3. So we've squared out that exponent. Now it's a complex fraction. We can clear the denominator in one shot. The most effective way is to multiply by the least common denominator, 4 over 4. Distribute it into the numerator where the red dot is, and we get 4 minus 1 after cancellation. Multiplying the denominator is 12, so it's 3/12, which is finally 1/4. So we get exactly 1/4 for the right-hand side of this equation. Now we look into the left-hand side. Here's where we'll do some actual calculus. So on the left-hand side, differentiate f of x. F prime at x is not too bad. And it's one of those weird chain rule kind of issues that seems to come up a lot in chapter 4, where the derivative of x minus 3 is a 1, so nothing big happens on the chain rule. But let's still show that step since we're still pretty much always practicing the chain rule. Bring that -2 down. New power is -3, so we've just differentiated the outer function. Chain on the derivative of the inner function, which is x minus 3, so copied in both positions. This derivative is exactly 1, so another mathematical miracle occurs right there. We don't have to do much with that. We can drop that factor. And simplifying this, because we're going to equation solve, means just write it as -2 over x minus 3 to the power positive 3. So that's the next component, the f prime at x. The mean value theorem says there will be a number c that solves its equation. And we have the two components in yellow. We just need to equate them now. But example 3 says, show that there is no solution to this equation. So we need to navigate to that contradiction on the next steps. But first, let's finish off this part, show that there's no solution to this equation we're about to write down. For f prime at c, I'll just leave this in terms of x still. -2 over x minus 3 squared. If you wrote it as c minus 3, no harm done. That's really a stylistic choice for doing this problem. Let's set equal to this part right here, which we meticulously calculated to be 1/4. So here's the whole equation. In solving this, we could just do a cross product. Multiply a cross equality this way and this way for those denominators, thereby clearing the denominators. That will imply that -8 equals x minus 3 to power, let me double check that. That looks like a 2. It was supposed to be a 3. Let me see if we can get a quick fix on that. Power 3. Then we multiplied that denominator to power 3 to the right-hand side. So that's our new equation. To solve an equation like this one, where there's a degree 3 polynomial, but in a factored form like that, you just take the cube root of both sides. So take the cube root of -8, the cubed root of x minus 3 cubed. -2 is at your left-hand side, equals cube root and power 3 cancel to give you x minus 3 on the right-hand side. And then finally add 3 to both sides, and 1 equals x. Which seems weird, right? Because we found a solution, so we have to ask what's wrong with that. Well, the problem with our solution is it's not in there. It's not in 1/4. The mean value theorem says there will be a solution in the interval from 1 to 4. If your b is 4 and your a is 1, like we solved in this problem, then that interval becomes 1/4. For c to be in 1/4, it has to be larger than 1 specifically and smaller than 4. So that's not in the interval. Since that's the only solution, we can say, therefore, there is no value for c in the open set from 1 to 4, which excludes 1 specifically and also 4. We didn't do anything wrong in the calculus nor the algebra, but there's a contradiction here. But maybe not. It says, why does it not contradict the mean value theorem? Here's the mean value theorem down below, just for a quick reference again. Mean value theorem says you will find that number c, but the mean value theorem also came with hypotheses that had to be satisfied. This is essentially the reason why we carefully checked the hypotheses when we did Rolle's theorem on example 1, when we did the mean value theorem on our last example 2. We painstakingly, we did a lot of writing, checked both hypotheses on example 2. Hypothesis 1 is that the function f is continuous on the closed interval from a to b. So let's focus on that first hypothesis, and that might answer why we don't actually have a contradiction. So the original function is f of x equals x minus 3 to power -2. Let's write out since f of x is 1 over x minus 3 to power positive 2. The form on top is good for differentiating, but the form on the bottom is a little bit better for spotting discontinuities. Since that's what f of x is, f has an infinite discontinuity at x equals 3. So right at the value 3, we have a problem. We did the average rate of change from f at 4 to f at 1. Also a good hint here, the open set is from 1 to 4. We can say that, therefore, f is not continuous on the closed interval from 1 to 4. It has that discontinuity right at 3. The vertical asymptote occurs at that value. And so that's why there's not actually a contradiction here. Mean value theorem guarantees you're going to find a number in 1 through 4. The open set from 1 to 4 is a better way to say that. If and only if you actually meet both hypotheses, every single one of them. We didn't meet continuity, and so that's why there was no guarantee for finding that number C. So that's what we'll say here to wrap this up. This is why there is no contradiction the first hypothesis was not met. So if we don't meet the hypotheses, continuity being just as important as the closed interval, just as important as differentiability, no guarantee that the conclusion is going to work as intended whatsoever. Caleb says, so on homework and exam, is there a need to do all that work to find the C if we're able to deduce that? So if you're able to deduce this, then yeah, you could say it doesn't meet the hypotheses of the mean value theorem, and that'd be a good way to end the problem there. Other questions at the moment? And maybe to answer the question a little bit more, Caleb says, so on homework and exams, there's there need to do all that work if we're able to deduce that the mean value theorem didn't meet the hypotheses. And I would say yes for the homework problem because it was really in two parts. The first part was to first show that no C exists. So we did that, ending right here when we made that conclusion. And the second part, really a part B to the problem, is explain why there's no contradiction to the mean value theorem. So think of this as really a two-parter problem. As the way the instructions were written, we really would have had to do both parts for this problem. But other questions at the moment? Okay, well, this is the full rundown on mean value theorem and also Rolle's theorem that we started out with. There's one more problem here, which is another mathematical application. But since I didn't ask anything quite like this one in the homework, we're going to skip to the next section 4.3. But if you're curious about this one, here's some consequences to the mean value theorem. Theorem 5, it's corollary 7. Theorem 5 says if the derivative is 0 for all x in an interval, then your function is constant. We usually start off like this. If f of x is 5, it's a constant function, then the derivative of f at x is 0, and that'd be 0 for all values in the domain. Theorem 5 kind of goes backwards, and it says, if you started by knowing the derivative was 0 for all values in a particular interval, then you can reverse the logic up to that line and say the function had to have been a constant, some constant. Then another application, these are just immediate consequences of the mean value theorem, is if your derivatives are completely equal on an interval, then the difference of the functions are constant, and that would allow you to prove a crazy trigonometric identity like this one. Again, this is an application that goes beyond the homework. And since we're a little bit limited on time, we'll skip this one for now. But if you're curious on seeing how the work looks like on this one, proving this kind of strange trigonometric identity, let me know and I'll be very happy to post the solutions to this. But for the moment, just so that we don't get too far behind on the schedule, we're going to go next to section 4.3, taking another look into local minimums, local maximums. So let's go to that next section. The section title here is How Derivatives Affect the Shape of the Graph. And there's lots of answers to that kind of open-ended question there. The first thing we're going to look into is the increasing, decreasing test. But when you look at that test, you might have a sense of deja vu. And if you do, good on you. It says if the derivative is positive on an interval, then f is increasing on that interval. If the derivative is negative on an interval, then f is decreasing on that interval. There's the first derivative test down below. Well, let's focus on one at a time, increasing, decreasing test to start. One thing that's kind of interesting here is we have actually used that test already in the notes. All the way back in chapter 2 in section 8, we were here. We had just defined the derivative when we did this particular section, 2.8. The derivative as now a function. So we stated the difference quotient limit here, but we were massively emphasizing that the derivative of f at x, if this limit exists, f prime at x is equal to specifically the slope of the tangent line of the graph. Because it's equal to the slope of the tangent line, if the function is increasing, that means the derivative is positive. The slope of the tangent line is positive. If the function is decreasing, then the slope of the tangent line is negative. But that's just said the derivative is negative. So using that information, we could take a graph like what we see here and sketch out the derivative. That's a derivative just right down below. Now let's capture this part right here. We'll lose the derivative portion and just focus on this piece here. In the view of the increasing, decreasing test. So once again, it said if the derivative of f at x is positive, that means f is increasing. So here we can say f prime is positive here. Wherever the curve is increasing, we have a positive derivative. It's increasing here, so the derivative is also positive in this domain from wherever that number is going off to the right. It looks like it was positive 1. It says if f prime at x is, sorry, let me change the color there. There we go. If f prime at x is less than 0, then the function is decreasing. And the logic also works backwards. If the function is decreasing, we had that statement there, then the derivative is negative. So f prime is less than 0 here, and less than 0 here for the derivative. So wherever we're decreasing as a function, negative derivative, wherever we're increasing, positive derivative. So that was the entire content of the increasing, decreasing test, but it also gave us something new as well. The first derivative test says, well, there's a local minimum right here. It's also an absolute minimum, but it happens to also be a local minimum. There's a local maximum here, and a local minimum here, tied with an absolute minimum. It says if the derivative changes from positive to negative at a critical number c, that's where the derivative is 0, that gives us the critical number, then you have a local maximum. And here's the derivative going from positive to negative. So we went from positive to negative on that derivative, and we absolutely have a local maximum right here. Likewise, if it changes from negative to positive, Here it is changing from a negative sign in the derivative to a positive sign in the derivative, as indicated down the notes. You will have a local minimum. That local minimum could also be an absolute minimum, like we see here on this particular graph, but it guarantees it's going to be a local minimum at least. If the derivative just doesn't change sign, then f has no maximum or minimum whatsoever. So that's the first derivative test, which is really just an extension of the increasing decreasing test. In section 2.8, we used it to construct the graph of the derivative. But now in chapter 4, we're going to use these same exact ideas to determine local maximums, local minimums. So that's what we're going to do exactly next on example 1. But any questions at all, folks, with kind of the refresher of these ideas before we give them a try? Okay, so for the first derivative test, when we apply that, we're really just using an application of the increasing decreasing test, finding where the curve increases, where it decreases, to get those local maximums and minimums if they exist. But as a process, the first thing we're looking for is a critical number for our function, which needs to be continuous. So that's really step 1. We're trying to find out where the derivative is 0 or the derivative does not exist. So we're back to dealing with those critical numbers. So with all that in mind, let me take a screen grab of this test here. We'll put all that into practice for this particular function, f of x. Okay, so here's our function. It's a degree 3 polynomial. If it was quadratic, you could use things like the vertex formula to find where the maximum and minimum might have been. But if it's degree 3, degree 5, or 7, and so on, the so-called vertex formula idea falls flat on its face. And this is the next thing that we would actually do. In fact, if you have a quadratic equation and you apply this test right here, you're just reverse engineering the vertex formula to find the maximum or the minimum. You get the same exact result. So that's kind of nice in a certain sense. We're going beyond the vertex formula from pre-calculus 1. But before we use the first derivative test, we're going to use the increasing decreasing test to find where the curve is increasing, where it's decreasing, which is also telling us where the sign changes from negative to positive or positive to negative. And that's what will give us our local minimum, local maximum values. But before we start any of that at all, we find the critical number c. So here's our step 1 in this entire process to find where the curve is increasing, decreasing. First, take the derivative. So we'll call this f prime at x, which is the world's best derivative, really, after we've done all of that work in chapter 3. This one's kind of a nice one to see. This becomes 6x squared minus 18x plus 12. So that's our full derivative on this one. We need to set it equal to 0 or find where it does not exist. But this derivative exists everywhere since it's a polynomial, so it's differentiable at any real number. That means we're really just trying to find out where the derivative goes to 0, which means we need to simplify it even further by factoring. As the greatest common factor 6, which we can pull out, leaving behind x squared minus 3x plus 2. Factors even further right here in a nice way. This becomes 6 times. We'll put an x here, another grouping symbol, and an x. And for this one, looks like we can go something like just say, not a plus, let's go with a minus 2, minus 1. Product of those numbers will give us the positive 2. The sum will be a negative 3. So that's the full factorization. And since we want to set equal to 0, we can just set it equal to 0 right here. So here's f prime at x, set equal to 0. We automatically get our critical numbers. This implies critical numbers can just be read off the factorization. One of them is 2. You could call it c equals or x equals. I'll leave it up to you as a judgment call. I'll go with x equals 2, x equals 1, are the critical numbers of our function f. So that's our first thing we want to do, find those critical numbers. Next, on step 2, we're going to find where the sign of the derivative is positive, find where the sign of the derivative is negative, and that'll tell us where the function is increasing and where it's decreasing. So decreasing means f prime, negative, increasing means f prime, positive. But notice we're going from an equality solving an equality to now an inequality. So we have particular strategies algebraically for handling that. Any questions before we go to solve the inequalities? Okay, well, back in the day when you solved inequalities like these, possibly in a pre-calculus 1 class, the idea is we sometimes call these cut points or critical points. Here we're just calling them critical numbers, but the idea is the same. They're going to separate out a domain. They're the numbers where the derivative is 0, which divide out the regions where the derivative is positive or where the derivative is negative. You first find where there's 0, and then determine the signs on the remaining regions. So one cut point at 1, another cut point at 2. That implies 3 different regions that we have to test. I like to put infinities on the end. That's optional. That's just a reminder for me in interval notation to include those. Now let's go with a color that pops out. We're going to use test points. Test points we will never use are the critical numbers themselves. We already know if we plug 1 inside of f prime at x, which is that here in a nice simplified form, we're definitely getting 0. Same with 2. We want to know where the derivative is positive, where it's negative. So we pick a number that's convenient in this region. 0 is probably the most convenient number ever. If x is 0, then that will imply plug it inside f prime at x. You can plug it right here. This is probably the best spot to put it in. You would get 0 minus 0 plus 12. So f prime at 0 is 12, which is positive. Now we tested one number on this region, but knowing at one single number it's positive tells us in this entire infinite interval, the derivative is always positive because it only ever switches to negative by hitting a 0, and that occurs at the critical number, 2 and 1. So we're always positive in this region, which means it's always increasing in that region. I'll use INC for a shorthand on increasing. Then we just go off to the next number, rinse and repeat. Any questions with the logic of this table here, this number line analysis? Okay, let's move on to the next region, the finite one. Pick a number between 1 and 2. First, Caleb says, so it doesn't matter what number you use. It does to an extent. For example, if I'm testing this region, you cannot use 1, you cannot use 2. But aside from that, no, it does not matter. You could use 1.000000123 if you were feeling fancy, or 1.5. Typically, we just pick a convenient number. So that's why I picked a 0 in this region instead of, say, like negative 99. But if you picked negative 99, you're not going to get 12, but I guarantee you it's positive. And that's all we need to find in our conclusion. So likewise here, 1.5 is probably a decent number to use. But other questions at the moment? Okay, so let's try out our 1.5 for this middle region right here. If x equals 1.5, then that implies the derivative of f at 1.5 equals, now you can plug it here, but I'd probably grab a calculator at that point. But it's actually more convenient just to plug it here. That's an equivalent algebraic form. It'd be 6 times 1.5 minus 2 is negative 0.5. Here, 1.5 minus 1 is positive 0.5. And I don't exactly care what the number comes out as. I just want to know its sign. And that's definitely negative because there's one negative inside that product. The moment we have negative, however, we can come back to this interval and say, for all numbers between 1 and 2, f prime is less than 0. But a negative derivative tells us the direction the function's going. It's going down. So that means it's decreasing in that range right there. Then just rinse and repeat. So on the next interval, you could pick any convenient number. I would say 3 is a nice rounded number to pick on this one. X equals 3 implies we'll get f prime at 3 equals, again, you could plug it here, but possibly be using a calculator. Way easier to compute here. You just get 6 times 3 minus 2 for a 1, 3 minus 1 for a 2. And even though that's 12, all we care about is what is the sign. It's positive this time, greater than 0, which means we're back to f prime bigger than 0 in this region. So it's back to increasing on that particular domain. So this is a degree 3 function. It has 2 turning points, goes from increasing to decreasing, and then from decreasing to increasing. That's all we wanted to resolve in part A, by intervals where it's increasing, where it's decreasing. So we can make a conclusion. Therefore, f is increasing on this interval from negative infinity to 1. Notice I wrote this as an open interval around the 1. At 1 itself, it's neither increasing nor decreasing. The derivative is 0. We knew that when we found the critical number. That's when the function's considered at rest, neither increase nor decrease. So we have to use an open parenthesis there, right at the critical number. Then use the union symbol to say this interval, union, or together with this interval, from 2 to infinity. So that's the increasing range, or domain rather, and is decreasing on just this finite range, or domain is a better way to say that, on the domain from 1 to 2. So increasing everywhere except for between 1 and 2 specifically. Now, the first derivative test has something to say from that. If you're going from increasing to decreasing, your curve has essentially that shape. That's not the accurate plot, but if I zoomed into the curve right around 1, it's going to look like that, going from increasing to decreasing. That's what's giving you the local maximum. So we have in part B already one important conclusion. We know where the local maximum is. Let's say here, local max at f at 1. That's the original function f. So we don't go to f prime at x. We go to that, the original f of x. F at 1 is 2 times 1 cubed minus 9 times 1 squared plus 12 times 1 minus 3, which boils down to, let's take a look at this. 2 minus 9 is negative 7, plus 12 is 5, minus 3 is 2 altogether. Let me know if my arithmetic went weird. Yeah, that looks about right if you grouped these up differently. So that's the local maximum value. 2, that's as high as it ever gets if you're around x equals 1. The next part of the first derivative test says if the sign of the derivative goes from negative to positive, or said differently, the function goes from decreasing to increasing, the shape of the curve has got to look like this now, roughly around 2, which means we're expecting a local minimum. And that's what the first derivative test is saying. There's a local minimum at 2. So local min, let's say not at, rather say of. There's a local minimum at two, but I want to say of value, whatever this comes out as. So better grammatical way to say is of f at two. Now we have to actually calculate that. That feels like a calculator operation at this point. Let's treat ourselves to a fast computation. If you're doing this in an exam setting, I'd encourage you to do the same. Don't get too bogged down on the arithmetic. That'd be 2 by 2 cubed minus 9 by 2 squared plus 12 times 2 minus 3. So the local minimum is exactly a 1. So we found our local max, our local minimum, and we did it without ever peeking at the graph. All we did was use properties of the derivatives, which absolutely influence the shape of the graph, and we just abused that to find where it's increasing, decreasing, and then this tells us where the local maximums and minimums will occur. If we ever had the derivative as positive, positive, that would mean the sign does not change, and that means no local maximum or minimum whatsoever. Well, any questions at all, folks? Finalizing this problem here. Okay, so this is one important technique when it comes to finding local minimums and maximums using the first derivative. So that's why it's called the first derivative test. But turns out there's another technique called the second derivative test. And this one's a really bizarre one because it says if the second derivative is positive at a critical number, you have a local minimum. And that always just kind of hurts my head a little bit when I read that. Positive to minimum looks like a typo, but it's not. Likewise, if the second derivative is negative, you get a maximum. And those seem to be backwards, but they're really in the right direction. The best way to make heads or tails of both of those at once is looking into issues of concavity. So that's the next thing we're going to take a look into, the so-called concavity test. But before we just do a concavity test, we have to talk about what do we mean by concavity in the very first place? So it says if the graph of a function lies above all of its tangents, it's concave up. If the graph lies below all of its tangents, it's concave down. And an inflection point is a point where it changes from concave up to concave down, or from concave down to concave up. An inflection point is where concavity changes, in other words. That's something that definitely deserves a visual. So to get a visual on this one, let's just reuse the function we already had. Let's plot this one. Let's call it f of x equals 2x cubed minus 9x squared plus 12x minus 3. And we had two critical numbers at 1 and 2, so we should be definitely around that range. Let's look at a picture around 1 and 2. This is also a decent check. We said the local maximum is 2. That checks out on the graph. The local minimum value is 1, and that checks out on the graph as well. So that's a kind of nice consistency there as well. But what we're mostly worried about is just this graph specifically when we think about concavity. So let's screenshot it right here. Okay, so this is the graph where we'll study concavity from. So it says, let's start off with the graph lies above all of its tangents. Well, for a statement like that, you should just start throwing down tangent lines. So I'll throw some tangent lines right here. Horizontal tangent lines are a good ones to start off because they're just easy to plot. And the graph lies above that horizontal tangent line there. If f lies below its tangent, it's concave down. Let's draw another tangent line. So here's another horizontal tangent line where the local minimum is, and the curve is below that tangent line. So right around 1, it's concave down. Right around 2, the graph is above, so it's concave up in that region there. But if it's concave up around 2, and then eventually becomes concave down around 1, somewhere in the middle, it changes, and that change is called the inflection point. A point on the curve, if f is continuous, and it changes from concave, say, downward to concave upward, is the inflection point. Those are not always easy to spot visually. You could put down a few more tangents. Say if you put a tangent that's based off that point. There's my dashed line. It looks like it's still concave down. If I put a tangent that's somewhere right around here, it looks like it's, this one's still concave up. Sorry, I got backwards. It's above its tangent line. So if it's above its tangent line, it's concave upwards. So somewhere in the middle, we need calculus to actually spot this. There's a point somewhere where concavity changes. So this is the inflection point. It looks like around this region, let me scroll or zoom out just a bit. Around this region, up to wherever that concavity point is, this looks like it's concave down. The graph is below its tangent lines. And from this region onward, it looks like it's going to be concave up. In other words, the graph lies above the tangent lines. So that's our definition for concavity. It's stated in terms of tangent lines, just kind of nice and curious in a way. Tangent lines we defined on day 1 of the class, and it keeps on making a strong showing in the comeback everywhere we've gone with calculus, it seems like. But any questions or comments at all, folks, thinking about these tangent lines? Okay, so far this is just the definition. Notice though, where we had its concave down, and where the derivative is 0, right where that critical number is, the horizontal tangent line, that is a local maximum, which seems counterintuitive to the concave down. And where it's concave up, that is a local minimum. So that's part of the secret of the last second derivative test. But before we get there, because we just defined concavity, that's an interesting topic in its own right. And here's the concavity test. The concavity test says, it turns out if the second derivative is positive, the graph is concave upward. So winding back to what we just drew, that's saying a positive second derivative is a guarantee that the graph of the function lies above its tangent lines. And that's kind of a remarkable fact in its own right. The reading does a good job to explain how these ideas come together, giving some nice graphs. Likewise, if the second derivative is negative, the graph is guaranteed to be concave downward. The graph will lie below its tangents, like on the last graph we were looking at. So that's a concavity test. We're going to use it on this logarithmic function here to find intervals where the function is concave up and intervals where the function is concave down. After we do that, we'll find points where concavity changes, which are points of inflection on the graph of the function. And as you do this problem, it should feel very, very similar to example 1. The only major difference is our conclusion is not increasing, decreasing, it's concave up, concave down. And the other difference is we go to the second order derivative, f double prime. So first step in this process, if you need to go to f double prime, you have to work your way there. First calculate f prime to start. So let's give this a try and see where we end up on this one. If that's our function, first derivative is not too bad, even though it's a chain rule. Logarithms and square roots turned out to be pretty forgiving for a chain rule. The derivative of a natural logarithm just takes the input you see here, drops it into a denominator. X power 4 plus 27. Then you multiply by the derivative of that entire input, x power 4 plus 27. But a lot of people take shortcuts here, and they just take that derivative and place it into the numerator, which is appropriate because if it's multiplying a fraction, that's in fact where it goes. So x power 4 plus 27, from the derivative of this, that's dropped to the denominator. The numerator is just the derivative of that same thing, so this becomes 4x cubed. So that's it, step one is over. We have to fight our instincts here to find the critical number to f prime. We do not set this one equal to 0. The reason being is the inequality is for f double prime. So we need to solve f double prime set equal to 0 so that we can do another number line analysis, get a sign chart going, find out where the second derivative is positive, where it's negative. So don't set that one equal to 0. We only needed this so we can go up to the second derivative. So that's our next step. First, any questions at all, folks, on completing the first derivative? Okay, well, the first derivative was the chain rule, and now the second derivative is quotient rule. So here's f double prime at x. For the quotient rule, first thing we need to do is differentiate the top. This will become a 12 x squared. Once we've differentiated the top, the pattern of attack is multiply by the denominator, unadulterated, just an x power 4 plus 27. Then go minus, now copy the numerator, 4x cubed. Multiply it by the derivative of the denominator, that's 4. X cubed again, and that's the whole thing for the numerator. Then we divide by that same denominator squared. X power 4 plus 27 squared. So that's our start. Because we're going beyond just calculating the second derivative, even if we were in chapter 3, we'd still need to simplify that. We need to do a major simplification on this with a numerator also factored. So let's begin by distributing this through. This becomes 12x power 6, and I need to 12 times 27. Let's cheat a little with the calculator here. Definitely way too late in the evening to do 12 by 27 in my head. So 12 by 27 comes out as a 324. So this is plus 324 x squared. So that's the first part distributed in. Let me fix this tab first. Then go minus 16 x power 6 divided by x power 4 plus 27 squared. Then it just keeps on going. So on the next step, we're going to get to negative 4 x power 6 when we combine our like terms. For factoring purposes, I think it's easier to just copy that term first. 324 x squared minus 4 x power 6 divided by x power 4 plus 27 squared. And then the algebra is still not done because, again, our goal is to solve an algebraic inequality. That's a lot of work we need to work through on simplifying this even further. First, let's do a numerical check on this. We know we can factor out an x squared. Let's see if we can pull out a 4 as well. 324 divided by 4 is, it works. We can factor that out to get an 81 altogether. So on our next step, take 4 x squared. Factoring 4x squared from this term just leaves behind an 81 minus x power 4 on this term. And if we get to x power 4 here, it just keeps on going. That term is going to factor as well. 81 minus x power 4. So x power 4 plus 27 squared down below. Now this piece is done, 4x squared. But this piece is a difference of squares. We can factor it like this. 81 splits as a 9 and a 9. Go plus and a minus. And x power 4 also splits as x squared. X squared. So that's a guaranteed factorization. And we're almost there, but this is one of those problems that feels like it just keeps on going. X x power 4 plus 27 down below. And new line, I feel like I should just restate f double prime at x at this point because we have such a long track of equalities we're going through. While the next line, 4x squared, is done. In algebra, a sum of squares only using a real number system does not factor. So that's automatically non-factorable. There's no way that's even zero. So 9 plus x squared. But there's plenty of ways that that equals zero, which tells us it's also factorable. It's just another difference of squares. Factors like this, 9 splits as 3 by 3. We go plus and minus, x squared splits as x and x. All of it's over x power 4 plus 27 squared. So that's the derivative. In its most simplified form, where simplified is by the context, you're about to solve some inequalities, which means fully factor everything, both numerator and denominator. The reason we're doing that is we set this equal to 0 next. This is pretty much what we did in example 1 with f prime, the first derivative. We need the critical numbers for f prime itself, so set f double prime equal to 0. And the only way this equation is ever going to be true is if the numerator goes to 0. So we ask ourselves, how could the numerator go to 0? You could plug a 0 there where you see the 4x squared. So x is either 0, impossible to get 0 here. There's just nothing we can plug in. So we just move on to the next. You could plug in a -3 here. Finally, you could plug in a +3 here. Those are the only ways for which f double prime ever goes to 0. So that's a lot of algebra and calculus already in this analysis. But it finally takes us to the third step. The third step is pretty much rinse and repeat exactly what we did on example 1. Let's take a peek at it just for a refresher to kind of organize our thoughts on this. For concavity, we're solving these inequalities right here, where the second derivative is positive or negative. For local minimums and local maximums, you're trying to find where the first derivative is positive or negative. That's why we stopped at the first derivative, we set it to 0, and got those critical numbers. Then those critical numbers are cut points. We placed them here, and we tested where the first derivative was positive or negative. We're just doing it all over, but now we're doing it for the second order derivative, f double prime. So that's our next step on this entire analysis. Well, I don't want to run it right down to the minute, so let's maybe just set this up. Here's what the next step is going to look like. We're going to write a numbered line from -infinity to +infinity with 3 cut points, which means we have 4 regions to test. Lots of work on this one. A cut at 0, a cut at -3, another at +3. So test here, 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 and here. We take values, throw them into the second derivative, determine if they're positive or negative, because positive means concave up, negative means concave down. So I think we could do it if we really rush, but I don't want to try to rush through a problem like this one. This one might be a good one to come back to, refresh what we mean by concavity, complete this problem, and then get to the inflection points. After we do that, we'll be ready for the so-called second derivative test coming up next. But sorry for splitting another problem in the middle. Turns out some of these problems are just longer than 15 minutes, it turns out, to get through. But any last questions or comments on the hard steps, getting through steps 1 and 2? Okay, well, thanks for your hard work on getting through these and great questions today. We've reviewed a lot of stuff. It's not just calculus, but lots of algebra. And I think this is the first time we've been solving inequalities. So if you can get through these kinds of strategies when you do them again on the homework, they'll be the same kind of problems on a real exam. Except on a real exam, I try not to make a problem that explodes this big. I try to make my questions a little bit short and sweet. But if you can get through a problem like this one on a homework problem, The exam 3 will be no big issue whatsoever. But have a great night, folks. On Thursday, we'll get right back to this one. We'll be finishing off section 4.3 and starting the next section 4.4 on Thursday's class. But have a great night, folks. I'll see you all tomorrow.